Welcome to this webinar on what's new in SolidCAM 2015 SP2. Last time, for some reason, we had some problems, so not many of you could watch the webinar completely. So what we have done is I'm going to run through all those things that was to be shown last time, and some very new things that also will be added up in this webinar. All right, so what we have new in 2015 is we have some nice new strategies in 5-axis for roughing, and that's called as multi-axis roughing. And there are some enhancements to the existing strategies and some very nice functions for converting 3-axis toolpath to 5-axis toolpath automatically. And we'll also see some nice things that have come up in swarfing, like rotating the swarf toolpath, providing a new kind of Gouge check for the swarf toolpaths. So there are a lot of things that we are going to see in this webinar. I'm going to start off with 5-axis roughing, or what we call as a multi-axis roughing. So we have this part over here with me, and we would like to cut this part from this stock. Okay, so the roughing has to be done using a bullnose tool, and it needs to be done completely. Why do we need multi-axis roughing? For example, if you look at this particular part, if I go to the top view, you can see that there are several areas on this part that are undercuts that cannot be done in one setup, which would need obviously multiple setups to complete. But with the multi-axis roughing, the entire roughing can be done out using just one strategy. You don't need anything more than that. So how does this work? I already have some toolpath. Let me suppress them. This works like this. So let me add multi-axis roughing. Okay. In multi-axis roughing and under strategy, we have got two different strategies. The first one is an offset strategy, which is similar to our contour roughing except for the fact that it is multi-axis. And then we have the adaptive strategy, which is basically mimics the toolpath that looks very similar to iMachining toolpath, but in full 5-axis. All right, so what we're going to do now is use the offset strategy, and we will use the strategy offset from floor. The principle of multi-axis roughing I will explain when it starts calculating, because it's going to take about a minute to calculate, and I'll explain to you the principle. In the meanwhile, let me add the floor surfaces. So I'm going to pick the floor surfaces. Now you can see that I have colored all my floor surfaces as green. So I'm going to use a new feature of picking the color from the model and finding all the faces with that color. So it has picked all these faces with the same color, and these are going to become my floor surfaces. Right. And then we have the wall surfaces. The wall surfaces I have put a different color, so it becomes easy for us to distinguish what is the floor surface and what is the wall surface. Now you can see there are several surfaces like this out here that look like a floor but are being considered like a wall. That is because SolidCAM works on a principle, or the multi-axis works on a principle that everything that is not the floor is considered as a wall, even though they could be parallel to the floor surface, or they would not be parallel to the floor surface. They are going to be considered as wall surface. So I'm going to pick from the model one of the colors of the wall and find all the faces of the model. Now these surfaces are my wall surfaces. You can see even the flat areas out here which are covering these bosses. They are being treated as a wall surface. Okay. I would like to keep 0.5 millimeter offset on the floor and 0.5 millimeter offset for finishing on the wall surface. I'm going to use a 12 corner radius to bullnose cutter. Okay. Levels, while entering, I want an entry safety distance of 5 millimeters. While exit, I don't need anything. 2 millimeters is good enough. You can see that in the clearance type, you've got the clearance type completely grayed out. You don't have plane, you don't have spear, you don't have a cylinder. That is because the tool is always going to be normal to the floor surface. So the retraction will always be normal to the floor surface, irrespective of where it is. So then it doesn't make any sense for us to define whether it is plane, spear, or cylinder. We just have to define the direction, which is basically normal to the surface, and how much is the distance that you want it to retract. So I'll say 35 millimeters I want it to retract, and a safety distance of 5 millimeters. That's good enough. Constraint boundaries. I could make the constraint boundary manually, or I could leave it to the software to determine an automatic constraint boundary for me. Toolpath parameters. The tolerance plays a big role here. Because we are roughing, we would like not to have a tight tolerance. So I'm going to use a tolerance of 0.1. My general thumb rule for tolerance versus the offset is that my tolerance is always 1/5 of the offset. So that's how I come to 0.1. So if I have 0.5, my tolerance would be 0.1. If I have 1 millimeter, my tolerance would be about 0.2. So it's 1/5 of the offset. Downstep can be defined in two different ways. You could have a constant step down, or you could have how many number of slices you want, or how many number of depths you want in this particular cut. So what I'm going to do is I'm going to introduce 2 slices. That means I want 2 depths into this, because just we would like to have a look at how the toolpath looks like. The maximum step over, we're using 12R2, so we need to go half of the flat area of the tool. The half of the flat area is 8 millimeters. So, sorry, the flat area is 8 millimeters, so half is 4 millimeters. Sorting, I would like to do one-way machining. The direction of machining is going to be climb, and we're going to sort by regions, which means it's going to finish one complete pocket and then only go move to the next one. That's the concept of regions. Smoothing, yes, I would like it to smoothen the corners, smoothen the final contour, and smooth also the links. If your side step is more than 50% or 60% of the tool diameter, then you have a problem that when the tool turns, tool makes a turn on the corners, when you have multiple tool paths, you will see that at the place where it's turning on the corner, it always tends to leave a triangular shaped material. That is because at that particular area, your side step is much more greater than what you have defined. Now, in order to eliminate that small area that is being left out, you can select remove corner pegs. So it just tweaks the tool path only at that corner to go into that area, remove the material, and come back, like what is shown on this picture. But we are using less than 50% now, so I'm going to remove the corner pegs option. Let's go to link. The first one I would like to ramp. So my ramp angle is 5 degrees, and I have got several ramping types here: automatic, line, helical, zigzag, and profile. I would like, you can pick anything, but I can keep it automatic because SolidCAM will put the right ramp. For example, in place where it is unable to do a helical ramping, it will put the zigzag line line ramping, or in case where it's neither able to do helical nor it's able to do the zigzag kind of a ramping, it will use profile ramping. So let's leave it to auto. Let's go to retract, approach and retract. The first one I would like to use ramp. That means it will use the ramp whatever is there. In the links, I would like to use ramp. And between groups, I want it to go to the rapid distance, use ramp. Between slices, again to the rapid distance, use ramp. Between regions to rapid distance, use ramp. Okay. Let's save this. Okay, and let's calculate. Right, now this is going to take about a minute to calculate because the part is pretty large. It's about 335 by 300 by about 15 millimeters in height. So it's a pretty large part. It's not a small part. Right, now coming back to our principle of machining on multi-axis roughing. How is this working? This works by a principle where the tool always remains normal to the floor surface. So the floor surface here is pretty much important, and the tool will always be normal to the surface. That's the green colored surface in our case, and it will always create the tool path looking normal to the surface. Alright, our first tool path is done. So what we are going to do now is have a look at how a tool path looks like. That's it. You can look at the tool path. I said 2 passes, so you can see how the passes have been taken. Every place where it is doing an entry, I am getting ramping inside. It is ramping into the material. Some places, because we have used auto ramping or auto strategy, in some places it's very difficult for it to provide helical ramping or different kind of ramping. So what it has done here is, you can see in some cases it is provided the zigzag kind of ramping because it's just not possible for it to provide helical ramping. In such cases, it decides on its own how it needs to ramp. Okay, look at this place here. Here it's just not possible for it to put helical ramping. So it's automatically putting the zigzag kind of a ramping into the material. So it's pretty smart. It machines exactly the way you want, and it uses its own smartness to decide which area to ramp and how it needs to ramp. So if we run the simulation of this, let's go to Solid Verify. Okay, and let's run the simulation. No. Right, so you can see that it completed the machining by cutting exactly the way I wanted to cut. So the principle is pretty simple. The tool always will be normal to the floor surface. Right, let's look at another machining where instead of going in the contour or offset direction, what I'm going to do is I'm just going to copy this operation and paste it, edit, and instead of the offset strategy, I will use the adaptive strategy. Now what happens in adaptive is it will try and maintain the step over at 4 millimeters, but in places that it's not able to maintain, it will drop down the step over between 4 and 3.2. So we have 2 step overs, maximum step over and the desired step over. And in this case, I just want 1 pass. And then you have got climb, step over, and conventional. Now depending on how your sorting is, if your sorting is one way, then it's always going to do climb machining. But if your sorting says zigzag, then the conventional step over comes into picture. The conventional step over basically is given because many users don't prefer the same step over when it is doing down milling. Rather, when it's doing up milling, they don't want the same step over of down milling to be applied to up milling. In such cases, they always go with a smaller side step than the down milling side step. So we also have given a percentage. We can say I want 50% of the step over when it's doing up milling or conventional milling, and 100% when it's doing climb milling. But since we are used one way, it's always going to be climbed, and it's always going to take 100% of the step over that we have provided. You can see that the smoothing also has disappeared from here. Basically, there's no smoothing needed, because in adaptive strategy, you just don't need to do smoothing because it's already a smooth toolpath. Remember the eye machining toolpath. Visualize it. It's always smooth. Okay. Let's go to link. Before that, let me switch off a link out here and then switch on the adaptive. My all other options remain the same. We are going to use ramping for approach and also for retract. All right. Let's save this and let me just check if the depth of cut was selected as 1. Okay, great. Let's save and calculate. Again, this is going to take about a minute. So coming back again, how this works. This works in a pretty simple manner. The tool, like I said, always remains normal to the floor surface and then cuts the wall in the direction of normal vector to the floor surface. So if your floor surfaces have an angle more than what the normal indicates, then probably it will leave some material. It doesn't eat into the walls, but it will leave some material. And then you can use the swarfing operation to finish off these walls. Where can you use these? Well, the immediate paths that come to me, to my mind, are basically structural components, where you have undercuts, where you have walls that are following the floor, all those kinds of paths, or maybe even conical paths with some helix running around them, you could use even there. So you can look at the part that's being shown to you, and any similar part that needs roughing in multi-axis toolpath is the best way to do it. So let's look at the toolpath, how it looks like. If you see this, you will immediately remember that this really resembles eye machining toolpath. You can see wherever there's ramping, and you can see there's a slotting kind of a motion happening out here, and when it's doing internal pockets, it does exactly like eye machining. Okay, what you're not seeing here is these connections. That is because both the surface and the connections are in green color, so now you will see it. You can see these connections, and as it comes to the corner, it again starts removing the corner exactly the way eye machining handles it. So very important and very useful feature to come in 2015 of SolidCAM. All right, let's move to some of the improvements that have happened in 2015 of SolidCAM. And what we are going to do now is we will look at the first one, and that's feed control. Feed control is a very unique feature. Okay, so let me first switch off some of the solid bodies. Okay, I have got a nice part, simple part, and I'm going to do a parallel to curve constant Z, parallel cuts constant Z toolpath with 16mm end mill. Okay, and what are the data? It has an RPM of 3,500 and a feed rate of 2,000. A depth of cut of 2mm and a spiral. So let's calculate this. Okay, that is calculated. Now let's look at the toolpath. Okay, now what we're going to do now here is I'm going to simulate and have a look at the table out here where the feed rates are. So 2,000 and the feed rate is constant 2000. You can see that there are no changes to the feed rate. They're all constant 2000. One of the reasons why this feature, feed control, was introduced was customers always say they reduce the feed rates when the tool goes into the corner. And there was no way for us to do it, so this new feature was developed. So what we're going to do now is we're going to edit this toolpath and go into a new function called as feed control. And in the feed control option, we have got the zone. The zone now can be defined in two different ways. The first way I'm going to show you is just pick the surface on which you would like the system or the software to reduce the feed rate. Okay, so these are 8 surfaces that I picked up. I'll say OK, and I want the software to drop down the feed rate to 50%. Okay, I want 50% of the feed rate only in the corners. And outside, I would like 100%. That means other than the corners, everywhere else, it's going to be 100%. Okay. Let's hit save and calculate. Let's run the simulation. And let's move and check how the simulation looks like. The feed now is 2000. Observe what happens when it goes into the corners. When it goes into the corners, the software automatically drops it down to 1000 millimeter per minute. So that's like 50% of the feed rate. Again, when it traverses over the corner, the next one is 2000, and again into the corner, it's 1000. Again, corners is 1000. Otherwise, it's 2000 constant everywhere. So this is a pretty nice and unique feature which helps you to reduce your feed rate in given zones. Like I showed you, the first zone I defined using the face itself. Let's look at another toolpath where I would like to switch on 4 bosses that I've created. Okay, these are the 4 extrusions that I've created. Now, in the feed control zone, what I would like to do is, I would like to define these bosses. So I'll pick from the model and find faces. So these areas, only I would like to reduce it to 50%. Now remember that these extrusions are not starting from the topmost point, but are starting from somewhere mid. So you can also specify the height from where you would like the software to start reducing the feed rate or start changing the feed rate. Okay, let's save and calculate. Okay, that calculation is done. Let's run the simulation. So you can see that when it's on the top, because the area is below, there's no change to the feed rate. The feed rate is constant at 2000 millimeters per minute. However, as we go down, you can see that as we go into the zone here, let me zoom. You can see that it's still not hitting the zone. So let's go down. Okay, it's still 2000. 2000. The moment it is into the zone, it drops down to 1000. So you can also define zones by extruded bodies or extruded solids. So you can change the feed rate not only by picking the surface of the model, but also using a completely different solid as a zone to control your feed rate. So this is another nice enhancement that we made in 2015. Okay, let's see the next enhancement. and that was a multi-blade. Now these are small enhancements that we made into multi-blade, apart from the fact that the engine of multi-blade is about 10 to 15% faster when it comes to calculation times or for the changes that we made. Okay, the change is in the link type. You can look at this toolpath, the finishing toolpath. When the tool enters the material for the first time, you can see there's no way you could control the entry. It goes directly or it plunges directly onto the blade. Now depending on the thickness of the blade, this could have damaged the blade. So what we have done in the blade finishing strategy is to provide a new type of link called as plunge arc. So it looks like as if it is plunging, but plunging very gently into the material by using an arc. Okay, let's calculate and see how the toolpath looks like. Okay, the calculation is completed. Let's look at how the toolpath looks like. You can see that it's provided a nice entry into the material. It doesn't directly dig into the material, but it starts with a nice radius, a gradual entry into the part. And the same is with the exit. The exit is also very gradual. It leaves the material using the arc, or what we call as a vertical tangent arc. Okay, let's go to another new enhancement that we have, and that's in Swarf. Let's open Swarf. Many of the customers who are using multi-blade also would like to finish the blades using swarfing. But the only problem they had earlier was if the multi-blade or the impeller had about 10 blades, then they had to make 10 toolpaths. There was no way you could take a swarf toolpath and rotate it. But now we've changed that. So let me edit the swarfing toolpath. And in rough and more, we have got an option to rotate the toolpath. So I can switch on and I can say 4 by 90 degrees. Say OK and calculate. Even the swarfing engine, the calculation engine, has undergone a lot of changes. It's much more reliable and much more fast in calculation. Okay, that's done. Let's check how the simulation looks like. You can see this is for the first blade. The first blade, it immediately goes to the next blade. We just picked up one blade as our geometry, and then we applied the rotation. Second, third blade, and then finally the fourth blade. Right. So a very nice enhancement that we made to our own swarfing engine. Now, staying in Swarf itself, let me open a part, and I'd like to show you some nice enhancements in the Gouge check area of swarfing. Okay, I have this part out here. It's basically a circular edge that is there that's driven around a circle. And if I calculate the swarfing toolpath, okay, and if you look at the, let's only keep the, remove the solid body, and I'll keep the surface only so that it's very clear on how this works. Okay, So let's run the simulation. You can see that the software is actually gouging into the part. Why is it gouging? To understand why it's gouging, what I'm going to do is again going to edit this part and create a surface which is lofted by two curves. Okay, so it's a simple loft, and I will switch off the outer surface and run the simulation with the current surface. You can see that swarfing works on a simple principle. What does it do? Irrespective of what you have as your surface for swarfing, what it basically does is it just takes the upper contour of the surface, the bottom contour of the surface, creates internally a lofted surface, and it actually starts machining that surface. So it's not gouging its own virtual surface that it has created, but obviously it is going to gouge the surface that we intend to machine, which is the outer surface. So how do we avoid this? Simple. The first option that we can use here is go to Gouge Check and click on Check Against Gouge Surface. Check Against Swarf Surface, sorry. In that we have got three options. The first one is degouge. That means just remove the gouge. I do not want the tool to gouge into the surface, and I'm ready to provide with some kind of a tolerance up to how much is allowed. So here I have said up to 10 microns gouge into the part is allowed. So if I now calculate it, yes. And if I now run the simulation, you can see that the software has pushed the tool out in a direction, in such a direction that there is absolutely no gouge. So if I now make, let's say, if I show you how the tool looks like, you can see that there is no gouge because the tool has been pushed out normal to the direction of the surface till the time that there is no gouge more than 0.01. However, you can look that it is leaving a lot of material here and leaving a lot of material on the top. Now, there are some customers who say, look, I do not mind to have gouges because that surface is just straight, but I'm worried about how much material is being left out. So I would like to control, or I would like to have a balance between how much it is gouging and how much it is leaving the material. So my next option inside gouging is to balance, and balance automatically. That means the software will decide how much it can leave and how much it can gouge. Okay, so we'll run that simulation also now. Okay, it's definitely going to gouge, but it's also going to leave little material. Okay, so it's like probably the first result itself. Okay. Right. Now you can see what it has done. What it has done basically is it is gouged inside to such an extent that it's actually keeping minimum material. It's not gouged completely like what we saw in the very first instance. The tool was touching this edge because that was a surface that it had generated. It is not doing that. It's come out but not completely out. So it is gouging but also keeping less material. The next option that we have is balance but within an allowance. That means I can specify how much it has to gouge or how much it can gouge. So I will say it can gouge by 1 millimeter, but it cannot leave material more than, let's say, 5 millimeters. So it's now going to find a place or a situation, a solution, where it is going to be pretty close to both of these allowances that I've specified. So I can now make another calculation. Okay, let's run the simulation again. It is pretty similar to the balance situation, that it can't leave more material, neither can it gouge much. So what it is trying to do is it's trying to find a middle ground between those two values. It may not stick exactly to that value, but it will try and find a middle ground between those two values and generate a toolpath in such a way that it doesn't exceed or go below the values that you have specified by too much of an amount. It will not be possible for it to maintain both the values, so it will try to find a middle ground between those two values. Okay, that's about swarfing. Let's go now to the most exciting release that we have inside 2015 of SolidCAM, and that's auto tilt. So let me open a part. Right, so we have a part out here, and this particular part, sorry, let me switch on. We have a part, and what I have done is I have generated in 3-axis or in HSM, I have generated a constant Z toolpath. Now, if you look at the height of this part, this is about 66 millimeters. So I will need a tool slightly more than 66 millimeters to machine this part, which means that a lot of vibration and chatter would be induced, because your L by D ratio is going to be higher. If you're, let's say, using a 10 ball nose cutter, your L by D ratio is going to be about 6. Now, what is the other best way? If you have a 5-axis machine, obviously you could generate a 5-axis toolpath. But generating a 5-axis toolpath on so many number of surfaces is actually a big job. So what we have inside SolidCAM is we have got converting an HSM toolpath to 5-axis. So I can select it. And what we had in the beginning was a simple conversion where we would define the source operation. We would define the link types, whether it's to be used from the source or new links to be applied. And we also had a big tool access control where a lot of things needed to be defined by the user. However, since 2015 SP2, we have released another one called as Auto Tilt. And Auto Tilt eliminates all those manual interventions that you need to convert a toolpath from 3-axis to 5-axis. So let's pick up the tool. Now I'm going to pick a small tool, or whose length is pretty small. Okay. So I'm going to pick this tool with an out of holder value of just 35 millimeters. Of course, I have a holder, but the tool is just 35 millimeters, which means an L by D ratio of 3, which would allow the software or the cutter to cut much more efficiently and faster without you having to worry about the chatter. However, the major cause of concern here is how do we check the gouge of the holder and what should the software do? Now, this was all the part of tool access control where everything was defined manually, but in the new version of SolidCAM, this is completely taken automatically. So I'm going to pick this tool. Tool access control, you can see most of the things are default. All those old options do not exist anymore. We have new options, and the defaults work perfectly. Everything is grayed out because we are not changing the links, leads and links. They're going to be the same ones which we are going to use from HSM. We're not changing anything. Okay, and in the clearance data, we have defined that it needs to be 2 millimeters away from the holder whenever there's a gouge. Okay, that's the value of clearance. All right, let's save this. So the moment I save it, my HSM toolpath is automatically suppressed, and I can then run the calculation of my toolpath. So it runs the whole thing in stages. First it will load the original toolpath, and then it will apply the collision check and its own collision check strategies and what it should do once it finds collision between any part of the tool with the part surface. And what is the behavior going to be? It's completely automatic. And most important, it's very fast. Okay, so you can look at a part like this. The calculation time could run in 40 to 45 seconds. You could what I can say is you can use whoever is in mold making industry and has a 5-axis machine can extensively use this feature. They could take a 3-axis toolpath, an HSM toolpath, and immediately convert it to 5-axis and run it on their 5-axis machine. So you are allowed to use smaller tools, smaller diameter as well as smaller length, which allows you to go deeper into the part without having to compromise on the L/D ratio issue. Okay, so the toolpath has been calculated, and this is how my toolpath looks like. You can see that no part of the leads and links were changed. Only thing that was changed was the axis, tool axis. So if I run the simulation, okay, I'm going to run the simulation for some time till it passes the 35 millimeter mark in Z. We will let it go down to, yeah. Now you can see that if I go to any one side, the moment it is detecting that there is an issue with the tool and the holder, sorry, let's run it again. You can see it's going down. The moment it goes beyond 35, that is because that's when you have the problem. You can see that the tool is now starting to tilt. Okay, you can see that the tool is now starting to tilt, and it will maintain this distance between the holder and the part geometry. And this is done all automatically. Okay, let's run it down further. And as it goes down, you will see that the tilt angle is actually going to increase. It's not going to remain same because it needs to avoid the holder and the part collision. So it automatically tilts itself. Right, so you can see that it was pretty easy and very powerful. The function is very powerful. It can just pick a 3-axis HSM toolpath, and depending on the holder geometry and the tool length out of the holder, it can convert immediately an HSM toolpath to 5-axis and give you, most importantly, give you a collision-free 5-axis toolpath, which is very, very important. Okay, so we are done with our features of 2015, and if you have any questions, or if you want to know something more, I'm ready for answering your questions. Aya?